In 9.7, we're going to look at applications of right triangles, but first we want to look at a few topics before we get into our application and solving problems with right triangles. The first thing is significant digits or significant figures, which you may be familiar with. That's typically used in science courses, and it reflects the degree of accuracy. So basically what you want to pay attention to when you have digits is pay attention to the decimal and the zeros. In this first number 12, you see that 12 has no decimal, no zeros. So the 1 and the 2, those are significant figures, and this has 2 significant figures. If I were to take 12 and add a 0.0, notice that that 0.0 is unnecessary. So if you're given data where there's a 0.0 or a 0.00, that tells you that you have to count those zeros as significant figures. So in this case, the 1, the 2, and the 0 are all significant, and we have 3 significant figures. If you have zeros between non-zero numbers, so notice that this is 3, 0, 0, 7, 2, so the zeros are between the 3 and the 7, then all of the digits are significant. So in this case, we have 5. And even if I were to add a decimal in there, it wouldn't change the number of significant figures because the zeros are between non-zero numbers. So we still have 5. So it's the last two cases that we have to be careful with. If you have zeros after the decimal and then some non-zero numbers, those first zeros are not counted. They're not significant. It's just the non-zero digits. So the 7 and the 2 would be significant, and we would have 2 significant figures. If you have a nice whole number like this 8,200 or integer, and there's zeros at the end, notice there's no decimal there. This is an ambiguous case, so we can only count the 2 non-zero numbers, so this has 2. Because you're not sure if you receive data that looks like this, whether the person had rounded the number or if 8200 is an exact number. So since you're not sure if it was rounded or it's exact, you can't tell what is significant about this number. So basically, if you're given data and you have to write your answer using significant figures, you would look at all the amounts of significant figures for each one of the numbers you have, and you choose the smallest. So if you're adding two numbers and one has 2 significant figures, the other has 3, you should answer with the smallest number, so 2 significant figures, just to make sure that we have this degree of accuracy. So moving on from significant digits or significant figures, we also have degrees and minutes. So sometimes you will see degrees written in terms of minutes or even seconds. Think of a clock where each hour is a degree. So our circles that we look at that are 360 degrees, that would be like a 360-hour clock, where each degree can be seen as 60 minutes. So if you want to translate 1 minute, it's going to be 1/60th of a degree. And we use this hash mark or accent mark or prime, if you're using math language, to indicate that this is the unit of minutes. So 1 minute is going to be equal to 1/60 degrees. Another way to go back and forth between degrees and minutes is to note that 1 degree is equal to 60 minutes. Now we can also talk about seconds. So 1 second is 1 second, and here, sorry, we're using these hash marks again. We're using 2 to indicate seconds. So 1 second is going to be 1 over 60 minutes because there's 60 seconds in a minute. That in turn would be equal to 1 over 3600 degrees. Or in other words, we have 1 minute is equal to 60 seconds, which makes sense if you're thinking in terms of time. In example 1, we want to convert this number to a decimal. So this is 73 degrees, 15 minutes, and 16 seconds. So what we want to do is we want to take the minutes and the seconds and change them so that it's a decimal. The minutes and the seconds, really this is 73. Oh, I don't like that color. This is 73 degrees plus 15 minutes. But if I want to change the minutes to degrees, I just divide it by 60, and I have my degree plus 16 seconds. Change it to degrees, I divide by 3600. So although we don't write the addition in between these numbers, it's understood that it's 73 degrees plus 15 minutes plus 16 seconds. When you put that in a calculator, you should get approximately, it's not going to give me an exact answer, and I get 7.2544, and the fours just keep repeating. So if I'm going to round this to 4 decimal places, it's going to be 73.2544 degrees. So really the minutes and the seconds are this decimal portion of your degree, if there is a decimal portion to your degree. So writing it in terms of minutes and seconds, that's a traditional way to write degrees if it's not a whole integer, if there's some decimal part to it. We typically don't use that form anymore, and we just stick to the decimal representation, which would be this answer that we have here at the end. Now, what if we had a degree in a decimal and we had to write it in terms of minutes or seconds? The 48 part, that's okay. We're only concerned with translating the decimal portion, which is 0.567, and it's still degrees. So if you take 48 degrees plus 0.567 degrees, you get 48.567 degrees. So I'm just splitting that up. And then we're going to translate the 0.567 degrees to minutes. So if each degree is 60 minutes, then all I have to do is, instead of dividing by 60 like we did in example 1, we're going to multiply by 60 minutes. So that would give me 48 degrees plus, and when I do the math here, I get 34.02, and that's minutes. Now notice that I have this 0.02 on the minutes. That tells me that I can actually break up my minutes into 34 minutes plus 0.02 minutes. And then I'm going to change the minutes to seconds by multiplying by 60. And here those are seconds. So finally we get 48 degrees plus 34 minutes plus, when we do the math there, it should be 1.2 seconds. And notice that there's a decimal part, this 0.2 on the seconds, but we won't break it down any further. It's sufficient to go minutes and, if necessary, seconds, and that's where you would stop. So we don't really need the pluses in there. We would write it without. So 48 degrees, 34 minutes, 1.2 seconds. So it may happen that you need to translate back and forth between degrees and then minutes and seconds. You might also have to calculate using the minutes or minutes in second form. In example 3, we have degrees in minutes, and we're supposed to add it. We want to write the final answer as a decimal. When you're adding, you want to line up the degrees and in this case, I don't have seconds, I just have minutes. So I have 53 degrees and 45 minutes. And then I have 29 degrees and 57 minutes. And I'm going to add these. So one thing we want to make sure we do is that we don't carry over the minutes to the degrees. We add them separately. So if I take the 45 plus the 57 minutes, I'll get 102 minutes. And the 53 degrees and the 29 degrees, when you add those together, you get 82. So we have calculated this, and we have 82 degrees, 102 minutes. But this is not in simplest form. The reason why is because of this 102 minutes. 60 minutes is a degree. So if this is 60 minutes plus 42, that would give us 102. I can change the 60 minutes to 1 degree. So that I can go ahead and carry over to the 82. So every 60 minutes can be changed to 1 degree. Once I do that, I have 83 degrees and 42 minutes. This would be our simplest form. In the last part of this, we're supposed to also write this as a decimal. So I have this in terms of minutes. I'm going to translate this to a decimal by taking 83 degrees plus 42 minutes divided by 60 to give me a degree. In my calculator, I don't actually have to approximate that because I get an exact decimal of 83.7. So this would be our decimal answer. Now we're going to start solving some right triangles. When we're asked to solve a triangle, what we're asked to find is all the angles and all the sides. So let's say I have this triangle ABC and I have the corresponding sides. So remember, a corresponding side is a side opposite. So the corresponding side to angle A is side A, angle B, side B, angle C, side C. And remember that angles and sides, they have this really nice relationship where the largest angle will correspond to the largest side. So in this case, since the 90-degree angle here at C is the largest angle, it's going to correspond to the largest or longest side, which would be C, and that's our hypotenuse. Now in example 4, we know that angle A is 34 degrees. So right away I can find angle B, which I don't know. Remember, the sum of the angles of a triangle, that would be 180 degrees. We already have a 90 and a 34, so we could just subtract that from 180. However, if you take 180 minus the 90-degree angle, the right angle, what's left over is 90 degrees. So I could also just take 90 degrees minus 34 degrees, because A and B are complements, to get 56 degrees. So I have all the angles. I need the sides. Going back to the problem, it tells me that side C is 12.7 inches. Okay. Let's see. So I need side A and side B. I have the hypotenuse. With respect to my angle A, if I were to find side A, that would be the opposite angle to A, and I have hypotenuse, so opposite hypotenuse tells me I would probably use sine. because sine of 34 degrees, make sure your calculator is in degrees, is going to be the opposite side, so that's going to be our A, over the hypotenuse would be 12.7. So now if you multiply both sides of this equation by 12.7, we have 12.7 times sine of 34 degrees is equal to A. And then once I put that in my calculator, I get that A is approximately 7.101749874. Wow, that's a lot. I would like to round this. Let's see. Oh, good. We have directions. It says round to 1 decimal place if it's necessary. So this would just be 7.1. And then that was inches. I'm missing side B. At this point, I could use the Pythagorean theorem. This is a right triangle. A squared plus B squared is going to be equal to C squared. And I have A, I have C, I just have to find B. So that's one option. Another option is to use the trig functions again. And since I already know how to use quadratic equation, I'm going to use, or the Pythagorean formula, sorry. I'm going to go ahead and use a different trig identity. So with respect to angle A, and where possible, you always want to use the values that were given to you, because what if I made an error when I was computing side A? So I have angle A. If I want to find side B, that would be the adjacent side to angle A, and I have hypotenuse. So adjacent hypotenuse is cosine. I could compute cosine of 34 degrees. That's going to be equal to B over 12.7. And then getting the B by itself by multiplying both sides by 12.7. It's 12.7 times cosine of 34 degrees. That's going to be B. Again, putting this in our calculator, I have 10.5287717. And we are rounding to 1 decimal place. This becomes 10.5. Probably shouldn't have written this so close. So I've solved this triangle. I've found all the angles and all the sides. Now I just want to do a quick check. I just want to look at this triangle and make sure that the largest angle, which is C, corresponds with the largest side. The smallest angle, which is A, corresponds to the smallest side. And then the middle one, B, corresponds to the medium length, which is the 10.5. So it looks correct. And that's just the visual check that you kind of always want to do when you're solving triangles. Let's try another one. In example 5, we have, again, this right triangle, ABC. We have side A, which is 45.2, and that's feet. We have side C, which is 82.7 feet. Okay, so it looks like I'm missing side B. I know that C is 90 degrees. And I don't really have to write that because you have that little box that indicates it's 90 degrees. So I have to find angle A, angle B, and I have to find side B. Well, it is a right triangle and I have 2 sides. So I would start off right away by using the Pythagorean formula that A squared plus B squared is equal to C squared. And I know that A is 45.2. I'm going to square that. I'm trying to find B. That's going to be equal to 82.7 squared. So our B squared is going to be equal to 82.7 squared minus 45.2 squared. And then when I put that in a calculator, it's probably going to give me it gives me an exact number, 4796.25. Taking the square root gives me approximately 69.25496372. I don't have any directions on how to round this. However, I do notice that side A has 3 significant figures and side C has 3 significant figures. So if I'm going to just go with the significant figures, I would round B so it's 3 significant figures. So I would round it to 69.3. And that was feet. Well, now I need to find a side. Again, remember we want to always try to use the sides that were given to us instead of the one we computed, because I could have easily made an error when I was finding B, and it would probably be just a calculator error. So if I'm going to use, let's say, side A and side C, because those are values that were given to me, so I know they're correct, then maybe I can look at angle A. So angle A with respect to side A, that would be the side opposite, and C would be hypotenuse. So I have opposite hypotenuse. This would give me sine of A equal to 45.2, the opposite over the hypotenuse. And that would be your 82.7. The thing is, we're trying to find A, not sine of A. We have sine of A. It's 45.2 over 82.7. So we're going to use our inverse trig function to get the A by itself. And this is what you would put in your calculator. If you don't have, also make sure that you're on degrees. If you don't have this key, sine with that negative one, so sine inverse, then you should use the second key with sine. And it depends on your calculator. If you're using, say, the classroom set of calculators, you would have to put in the 45.2 divided by 82.7 first, and then do second sine. But other calculators, you would just do the second sine and then put in the 45.2 over 82.7. So something to be careful about. Once I do put this in the calculator, I get my angle A is approximately, again, we're in degrees, so 33.1309095 degrees. And I'm using significant figures, so I just have to round that to 3 significant figures, and it'll be 33.1 degrees. So now finding B is easy enough. We just take the 90 degrees minus the 33.1 degrees. And we should get 45.2. Can I not do math today? 56.9. I don't know. So fired. 56.9 degrees. So that would be this angle here, 56.9 degrees. So we got all the angles, we got all the sides, and we are done solving that triangle. We're going to do one last triangle because this one is written in terms of the angle measure being degrees and minutes. So the problem with having it in degrees and minutes is that you are going to have to first translate it to its decimal form so that you can actually put it in a calculator. We have that angle A is 34 degrees and 28 minutes. So since angle A is given as degrees minutes, then we have to write angle B in terms of degrees and minutes. And we don't have to do anything for angle C. We already know that's 90 degrees and 0 minutes, so I'm not going to write the 0 minutes. I have side A is 25.9 centimeters. And that's all I have. So to find B, I have to subtract 34 degrees and 28 minutes from 90 degrees. Okay, so I'm going to have to borrow from 90 because this is not going to work. So I just don't borrow 1, as this is a 0 minutes. So I'm not going to borrow from the 9 and have 8 and then 9 and then bring it over and have 100 minutes. And that's because every degree is only 60 minutes. So this 90 degrees is actually 89 degrees plus 1 degree. So what I could do instead is I could change that to 89 degrees and bring the 1 degree over to the minutes. Each degree is 60 minutes. So now when I subtract the 34 degrees, 28 minutes, what I get is, again, we subtract them separately, so 60 minus 28 will give me I can't do the simplest math, 32. I'm trying to do this in my head instead of using a calculator, and then I get 55 degrees. So 55 degrees and 32 minutes. I have all the angles. Now I need the sides. I only have one side, so I can't just use the Pythagorean formula. I'm going to have to use a trig function. If I'm using angle A, then that means I'm going to have to translate that from degrees and minutes to just degrees with decimal. So 34, because I have to put in my calculator, and I can't put degrees minutes in my calculator, plus the 28 minutes, if I divide it by 60, that will give me the degrees. And that's approximately, let's see, 34.4666666. The sixes just keep repeating, and that's a degree. So the 34 degrees in 28 minutes is approximately 34.4666667 degrees. So with respect to A, I have the side opposite. I need the side adjacent, or I need the hypotenuse. So I could choose tangent. Tangent of 34.4, that would be opposite over adjacent. I could do sine and solve for the hypotenuse. So if I did use sine of 34.46666, and I'll just go out that many decimal places. You don't want to round it too much because it might really mess up the value. That's going to be opposite is A. Oops. Opposite is 25.9. over hypotenuse, which is C. So I'm going to solve for that C value. Now you got to be careful because if you multiply both sides by C, you at least get rid of the fraction. This becomes C times sine of 34.4666667 degrees. Again, I'm trying to get something I can put in my calculator, so I have to get the C by itself. In this case, you would divide both sides by the sine of 34 blah 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 degrees to get C equal to 25.9 over sine of 34.4666667. Again, you could round that degree that we're putting into the sine function a little bit more, but don't write 34.5. That's rounding it a bit too much and your values will be really off. So I get 45.765. It says round to 1 decimal place if necessary, so I'm just going to stop there. Side C, our hypotenuse, it looks like it's going to be 45.8. And then that was centimeters. Okay, so now the only thing left is to find side B. Again, we could use the Pythagorean theorem right now. I can do the C squared is equal to A squared plus B squared. Or I could try another trig function. So since I'm looking for the side adjacent and I have hypotenuse, I could try cosine of 34.4666667 degrees. So cosine of A is going to be the adjacent, which I don't have, over my 45.8. 45.8 times cosine of 34.4666667. That's what I'm going to put into my calculator because that's going to be equal to B. Cosine of 46. Oops. When I put that in my calculator, I get approximately 37.76. And I won't do the whole decimal that I have. It says round to 1 decimal place. So if I'm rounding to 1 decimal place, that should be 37.8 centimeters. Okay, so let's do a visual check. Smallest angle is A, smallest side is side A. Largest angle is C, largest side is C, and then B is the middle. So there might be like a minor error with the rounding and stuff, but that should be close enough for accuracy. Let's move on to another thing that may come up as you're solving some word problems with right angles, and that would be the angles of elevation or the angle of depression. So basically, when we talk about an angle of elevation, and you can look at this first diagram here, we could see this person. The horizontal line is if that person's looking straight forward. Now, if the person has to look up at an angle to see something up high, such as an airplane, that would be an angle of elevation. If that person has to look down to see something, say on the ground, like in this case a dog, that would be an angle of depression because you're going down from the horizontal. We do have to be careful about who's looking. In this next diagram, we have an example of a person looking at an airplane. So since this person has to look up from the horizontal, in this case, we have our horizontal line. They're looking up 40 degrees and they're seeing an airplane. And that would be an angle of elevation because the person's looking up. But what about the pilot who's actually in the plane? He has his horizontal sight looking straight ahead. To see the person on the ground, the pilot's going to have to look down. So that would be an angle of depression. So just make sure that you're clear on, are you going up? Are you going down when you label your angles? Notice in this particular diagram, the angle of depression and the angle of elevation, they're the same. So going back to some properties in geometry, I'm going to extend this horizontal line for both the plane and the man. So they kind of look parallel, like parallel lines. This line that is forming those 40-degree angles, the line that represents the angle of depression and elevation, that's a transverse line. It's intersecting two parallel lines. So whenever you have a line that intersects two parallel lines, and look between the parallel lines, you have these interior angles. So the alternate interior angles are going to be equal. So necessarily, if we look at the plane and we have our angle of depression as 40 degrees, since this horizontal line is an angle of 180 degrees, it must be true that the other angle is 140. Likewise, going where this person is, if we look at the supplementary angle, it has to add up to 180, so that would be 140 degrees, which makes sense because these are alternate interior angles as well, so they both have to have the same measurement. But something else comes up as well. Going back to geometry, if you have, and I'm just looking at the plane, if you have two lines that intersect, and it doesn't matter if they intersect at right angles or any angle, what's going to happen is the opposite angles are going to be the same. So we would have 40 degrees and 40 degrees. And if this larger angle is 140, then the opposite is also going to be 140 degrees. So these properties may come in useful when we're working through some of our word problems. When you do work with a word problem and you're not given a sketch, you're going to have to draw your own sketch because these are pretty difficult to figure out without a picture. So basically draw a sketch and label it with the given information, and then use the sketch to write an equation, solve the equation, and check that the answer makes sense. In example 7, we have a guy wire that's attached to the top of a vertical weather tower. So if you don't know what a guy wire is, it's a support wire that attaches itself to the object, and then typically it'll be attached to the ground to stabilize the object. A form of a guy wire would be the cords that you attach to tents to stabilize them. So we have this guy wire, it's attached to the top of a vertical weather tower to stabilize it. And the distance along the ground from the wire to the base of the tower is 212 feet. The angle of elevation to the top of the tower is 27 degrees. How tall is the weather tower? Round to the nearest foot. So that's a lot of information. I'm going to start drawing my picture. Well, first of all, I have this weather tower. So I'm just going to pretend that this is my weather tower. And we have this wire that's attached to the top of this vertical weather tower. And it's anchored to the ground to stabilize that. So the distance along the ground from the wire to the base of the tower is 212 feet. Notice that I've also formed a right triangle. The angle of elevation, so here we're talking about elevation. The angle going up to the top of the tower is 27 degrees. That would be this angle here. If the ground is the horizontal, this is the angle of elevation. And that would be 27 degrees. We want to know how tall the weather tower is, so I'm just going to call this X. I've got a right triangle. With respect to 27 degrees, I have the side adjacent. I want the side opposite. So when I think of opposite and adjacent, I think tangent. If I take tangent of 27 degrees, it's going to be equal to the opposite, which is X, over the adjacent side, which is the 212. And now if I multiply both sides by 212, then 212 times tangent of 27 degrees, that's going to be the height. In my calculator, I get approximately 108.019. Do I need to keep going? Oh, okay, we only have to round to the nearest foot. So if I round it to the nearest foot, it looks like it would be 108 feet. Typically, we would write a sentence answer. The tower, or the height of the tower, maybe? The height of the tower is, and I'm going to use about because we rounded, 108 feet. The height of the tower is about 108 feet tall, but I'm just going to leave it as 108 feet. So there's my sentence answer. When you have a diagram and you introduce a variable, so notice that I call the height of this tower X. Typically, when we introduce a variable, we have to define it. Like I would say, let X be the height of the tower. But in the case where we have these really nice right triangle diagrams or nice diagrams, it's clear what X stands for. So there's no need for you to define it. Let's try another example. We have a 35.10 foot building. Now notice that that 0 is not necessary. I could have written 35.1. So that gives me a hint that I'm probably going to have to use significant figures to round. So a 35.10 foot building casts a shadow of 38.62 feet along the ground. Find the angle of elevation of the sun. Okay, so I noticed that the 35.10 and the 38.62, they both have 4 significant figures. So I don't have any instructions on how to round, so I'm going to assume that I'm going to round to 4 significant figures. Let me draw a picture. We have a building. Here's my building. There's my little, oh, I'm not going to put windows. And the building is casting a shadow on the ground. The shadow is 38.62 feet. The building is 35.10 feet. We're supposed to find the angle of elevation of the sun. So if you think about it, the sun's going to be behind the building, it's going to be shining down, and it's going to create that shadow. So we're going to have this angle of elevation of the sun. So if you see of the sun or to the sun, it means the same thing. Elevation means going up. So that angle from the horizontal ground is going up, and it's an angle of elevation. However, if you had seen it another way, if you had thought of the sun as having the horizontal, well, I guess it would have to be really behind the building. Then you could look at this angle of depression as the angle that we need to find. These would actually give you the same value because we've got parallel lines. The alternate interior angles are going to be the same, so these would be the same. Now I want to find that angle. Again, I'm just going to use X. With respect to x, I have the side that's opposite, and I also have the side that's adjacent. So I have opposite, adjacent. That tells me probably tangent, but again, you don't have to use tangent. Tangent of x is going to be the opposite, which is the 35.1. I don't need that 0 when I'm computing, over the 38.62. Now, since we're trying to find x, we need to get rid of the tangent. That tells me I'm going to use that inverse and do tangent inverse of 35.1 over 38.62. Again, that would be your second tangent in some calculators. And once we put that into our calculator, I have that x is approximately 42.266 I'm going to stop there because I'm doing 4 significant figures, but let me just double check one time. And again, this is going to be an angle. I don't know if you can hear that rooster right outside my window, but it's super irritating. I'm going to double check this real quick. 38.62 and 42.26630,382. Yeah, I'm going to stop there. 4 significant figures would be 42.27. So the angle of elevation, is about 42.27 degrees. Don't forget that degree on there. So the last thing we're going to talk about in this section is what we call bearing. Bearing is just a navigation term. It's just the direction that you're going in. So it's typically used for airplanes or for boats. There's 2 common ways that we talk about bearing. So that would be so that somebody can find, let's say that you're in a boat and you're lost at sea. If you have your bearing, you could let Coast Guard know, hey, this is my bearing. And they can find you. Maybe. It's pretty hard to find people in the middle of the ocean though. Okay, so there's 2 types. One would be if you're just looking at the north line. Now, if we look down at this first diagram here, our cross where we have north, south, east, and west, if we were just using north to guide us, we would be looking at the north line and we're going to move clockwise. So this is not the usual angle and standard position where you're going counterclockwise. You're starting from your north line and you're going to go clockwise. So you're going to go down and around. And you're going to come up with a degree from north or due north. So in this example, I'm looking at 127 degrees from the north or due north. So I would write this as 127 degrees due north. But since it's just referring to the north line, oftentimes you won't even see the due north. You'll just see the degrees. So if they're talking about bearing and they only give you degrees and nothing else, you can assume it's due north. That is one way to measure our angles. The other way to do bearing is using the north-south line. So we're going to look at that same bearing in this next diagram. If we look at this north-south line, and notice that I have the same bearing as I did in the first diagram. Whatever this object is, it's going in the same direction as the first diagram. Another way I could describe that is choose either north or south. You're going to choose the one that is closest to your object and that would be south. So from south, if we go 50 degrees towards the east, then that's another way that we can describe that same bearing. So you're going to choose to start with either north or south. You would choose the one that's closest to your angle. So you're going to form an acute angle. In this case, it would be 53 degrees. Notice that this is still 127 degrees. So this is just describing the 127 degrees due north in a different way. And in fact, using the north-south line is more common nowadays than using due north. So I'm going to use S for south. We don't have to write out the word south, but you can. And then from south, I'm going to go 53 degrees towards the east. And we'll just use a capital E for east. So this would be another way to describe bearing. Let's practice that in example 9. It says sketch the bearing, and this is just a sketch. In part A, it's 290 degrees. Notice there's no letters like north, south, east, or west, or N, S, E, W. So I assume this is due north, even though it's not written, which means I'm only using the north line for my angle measurement. I'm only using the north line, but I prefer to still draw the whole direction cross. If I'm going 290 degrees, so remember we're starting at north and we're moving around from north. So that would be a 90, 180, 270, and a little bit more. And then this would be the sketch of my bearing. And I've gone this direction clockwise. I should label my angle, which would be 290 degrees. So this is 290 degrees due north. In part B, I see an N and a W, so that tells me I'm going to use the north-south line. Again, draw my cross. I have north, south, east, and west. And notice that when I was doing part A, I didn't bother to put in the E, W, and S because I'm just using due north, so I only needed the N. But here I'm going to start at north, and then I'm going to go 80 degrees to the west. So if we start at north and we go 80 degrees to the west, it's almost to 90 degrees, but not quite. It'll be something like this. It's actually the same as in part A. It's just described a different way. So we're going, in this case, we're going in a counterclockwise direction. So if you're doing part A, if you're doing due north, you're always measuring your angle clockwise. However, if you're using the north-south line, you could be going clockwise or counterclockwise because you're trying to go to the smallest angle. So this angle here is 80 degrees, and that is a diagram of a bearing north 80 degrees to the west. Part C, we have south 48 degrees, 10 minutes east. Now, whenever you're sketching a bearing and you have minutes, it is not necessary to translate that to decimal. And that's because this is 48 point, a very small amount. It's a 48 point something degrees, and we're just drawing a sketch. So it's sufficient just to keep it the way it is and estimate where 48 and a little bit more would be. So we're starting in the south and we're going towards the east. So you can just draw the S and the E, or you could put them all in. And we're going to go 48 degrees in 10 minutes. So this is 48 degrees and just a bit more. If I were to sketch that, that would be a little bit more than halfway between south and east. So maybe here, kind of looks like it. And this is my angle of 48 degrees and 10 minutes. Okay, let's work on our last problem in this section. In example 10, a plane flies 1.5 hours or 1.5 hours at 110 miles per hour on a bearing of 40 degrees. So I notice that there's no letters there, it's just 40 degrees. So I can assume this is due north. Then it turns and flies 1.3 hours at the same speed on a bearing of 130 degrees. How far is the plane from its starting point? Round to 1 decimal place if necessary. So first of all, I have no idea. I'm going to draw a sketch. I'm going to start with a cross. Now, I'm going to start out due north. I'm going to go a little bit like 40 degrees. So my angle is going to be sort of up. I think I'm going to have my cross be kind of down here. 40 degrees is not quite half. So I'm flying 1.5 hours at 110 miles per hour on a bearing of 40 degrees. And this is 40. Plane's going to turn. And then it's going to fly. So since it's turning, I need to draw another cross where it's going to turn. Because it's going to change direction and I'm still doing my bearing in due north. So I have to draw a new north. It's going to go 130 degrees due north. So we have 90 plus 40, maybe something like this. How long am I going to draw this line? No, I'm going to stop there and read my problem for a second. So on the first part of the trip, it's 1.5 hours. Second part, it's 1.3 hours. So it's a shorter amount of time. So that line should be a little bit shorter than my first one because the speed of 110 miles an hour is going to be the same. I'm just going to erase a little bit of this. I'm going to try to make your diagrams as representative as possible. And now remember that this angle is 130 degrees. The question is, how far is the plane from its starting point? I need to find this distance. I'll call that x. That's what I need to find. I can figure out the length of the two sides because the distance, which would be the length of the sides, are going to be equal to the rate that the airplane travels times the amount of time that it's been traveling, because distance is rate times time. I just want to double check and make sure that my time measurements are consistent. So I have hours, 1.5 hours, and miles per hour, which is a good thing because if they were different, then I would have to adjust and have them both be hours or both be whatever the other units are with respect to time. So I don't have to do anything here. The first line, time is 1.5, speed is 110. If I put that in a calculator, I get 165, and this would be miles. On my diagram, I'm going to write 165. The second leg of the trip, we're going 1.3 hours, same speed, 110. In my calculator, I get 143 miles. And that would be this length of my triangle. So it would be really nice if this were a right triangle because I've got two sides. I would just have to find x using the Pythagorean formula, but I don't know if I have a right triangle. It kind of looks like where we have the north 130 degrees, kind of looks like that might be a right triangle. So this is where you're going to use those properties that we talked about. So notice that my north lines, if I were to extend them, these would be parallel lines. And the first leg of the journey is a line that intersects the parallel lines. So if I have 40 degrees on one side of this line, I'm going to have 40 degrees on the other. Whoops, I put 40. And then notice that if we go up to the top where we have the north, the 130 degrees, that north line is 180 degrees. So if I've gone 130, go a little bit more, say another 50 degrees, then that length here will be 180 degrees. So if I take the 40 plus the 50, that gives me a right triangle. So now that I know I have a right triangle, I can just simply use, I don't even have to use any trig functions. I can simply use the Pythagorean formula to note that x squared, which is our longest side, that's our hypotenuse, it's across from the right angle, that's going to be equal to 165 squared plus 143 squared, which means my x squared is going to be equal to 47674. And if I square root, I get approximately 218.34376. Oh, hold on. Round to one decimal place. Oh, I can stop and just write 218.3. Our sentence would be the plane is about 218.3 miles from the starting point. So that is it for this section.